Hello, good day, everyone. It's another wonderful time, and we are starting another series of lectures on geometrical optics. And today we shall be introducing what lenses are. In our everyday activity, we encounter the images formed by lenses. As you can see, we have a young man with glasses hanging down his nose, a woman with a contact lens and a camera. And we also encounter lenses in overhead projectors, opera glasses, and magnifying glasses that we use in performing simple experiments in the laboratory. So at the end of this lesson today, you should be able to define what a lens is, state and explain the common terminologies we use in describing a lens, and state the types of lenses that we have and define the power of a lens. But before we go on, we will remind ourselves of the laws of reflection and refraction. The law of refraction states that the incident ray, the reflected ray, and the normal to the surface all lie in the same plane, and the angle of reflection equals the angle of incidence. The law of refraction states that when light travels from a material with refractive index n1 into a material with refractive index n2, the refracted ray, the incident ray, and the normal between the two surfaces, between the two materials, all lie in the same plane. It's also known as the Snell's law, which is expressed as n1 sine theta 1 equals to n2 sine theta 2, as shown on this slide. Now, fully into what we have today. What is a lens? A lens is simply a piece of transparent material such as glass, plastic, quartz, fused silica, or liquid with one or more curved surfaces in which the extent and nature of the curvature of the surface determines the effect it has on a beam of light. Lenses form an image by refraction of light at its two boundary surfaces. Unlike mirrors, take note, the lenses bend light through refraction and not reflection. Common terminologies used in ray optics. A lens has two curved surfaces. Each of these curved surfaces has what we call a curvature, as you can see in the diagram on this slide, as indicated on it with letter C, which between the optical axis and C is the radius of curvature, and the radius of curvature is the length of the curved surface of the lens. Now, the line joining the centers of curvature of the two curved surfaces is called the principal axis. It bisects, as you can see in the diagram, the lens horizontally into two equal halves, and the point where the principal axis intersects the two refracting surfaces is called the front vertex and the back vertex. The point F, as indicated in the diagram, where the set of rays parallel to the principal axis is caused to converge or diverge, is called the principal focus. The point on the principal axis for which the rays passing through are not deviated by the lens is called the optical center, O. The distance between the focal point and the optical center of the lens is called the focal length of the lens. That is, from the optical center on the optical axis to the focal point is where you have your focal length. The plane perpendicular to the principal axis of the lens and passing through the focal point is known as the focal plane. When a point or linear object is placed on one side of a convex lens beyond the focal plane, an image is formed on the opposite side of the lens. The distance from the front vertex to the object is called the object distance, denoted as S, sometimes U, and sometimes D naught. And the distance from the back vertex to the image is called the image distance, denoted as S prime. Sometimes we use V, letter V, or D subscript I to represent the image distance. Types of lenses. Basically, we have two types of lenses: converging lens and diverging lens. A converging lens is a type of lens that is thicker at the center than at the edges. When rays of light impinges on it, the rays from the left that are near to the principal or optic axis that is your paraxial rays, and the parallel to it converge to a single point on the axis after emerging from the lens. As you can see, the focal point f2 and f1. Converging lenses are also known as positive lens or convex lens. Diverging lenses, on the other hand, are thinner at the center than at the edges. This causes light rays which come in parallel to the optical axis from the left to diverge as if they came from a point on the left hand side of the lens. And you see the convergence of the focal point on the left as f1. The diverging lens is also known as concave lens or negative lens. Common shapes of lenses are biconvex, planoconvex, and convex meniscus as shown on this slide, and we have the common concave lens as biconcave, planoconcave, and concave meniscus. Before we conclude today's lesson, we define the power of a lens. The power of a lens is the measure of its ability of a lens, to change the curvature of the wavefront at the lens. It's often calculated with P equals to 1 over F, where F is your focal length. The power of a pair of lenses of focal length F1 and F2 placed in contact is the addition of their individual powers. Mathematically, is expressed as 1 over F equals to 1 over F1 plus 1 over F2 equals to P equals to P1 plus P2, where P1 and P2 are the powers of the two lenses respectively. In summary, we have learned today what a lens is, and we have defined it as simply a piece of transparent material such as glass, plastic, quartz, fused silica, or liquid with one or more curved surfaces in which the extent and nature of the curvature of the surface determines the effect it has on a beam of light. We equally stated that we have two types of lenses, which are converging and diverging lenses. Primarily, the unique difference is that converging lens is thicker at the center than at the edges, equally known as convex lens, and diverging lens is thicker at the edges than at the center, also known as concave lens. And we stated that the power of a lens is the reciprocal of the focal length, which is the measure of its ability to change the curvature of the wavefront at the lens. Thanks for listening. Have a wonderful time.